Hi, I'm Trevor.
Hi, I'm Gavin.
Hi, I'm Parma, and today we're going to be talking about smallpox. Don't worry though, only the good parts, the eradication of smallpox. So, an important thing to remember about the eradication of smallpox was that it was a very politically charged issue, further complicated by the fact that the World Health Organization was feeling very sad and salty over their latest failures at eradicating other viruses. That being said, there were three important reasons that motivated even the dejected workers of the WHO to promote worldwide support for the eradication of smallpox. First, smallpox is highly visible, like you can literally see a rash on someone. And this makes it so that the disease is much more easy to treat because it can be noticed and symptoms often present themselves very close. Also note that HIV is not like smallpox and is not immediately visible. The second important reason is that it only is transmitted between humans and it does not transmitted between animals. So the cat gets to keep one of its 9 lives this time. And basically because of this, it means it's a lot easier to contain because it can't be disseminated by an animal vector. Third, they didn't have to waste time creating a vaccine as there was already an effective vaccine made. And this allowed a lot of people to be vaccinated and the disease to be eradicated a lot faster. So it was all of these reasons combined that made smallpox a very effective candidate for worldwide eradication. But even with all this knowledge, there were still lots of World Health Organization workers who were being difficult. So, the WHO Director General proposed a 1966 assembly to debate the issue. So they met, with half of them supporting eradication and half of them being like, or not. And so after lengthy debate, the WHO Director General decided for them that, yes, they would eradicate smallpox, and yes, it would cost $300 million, but at least 1/3 of those would come from international contributions. So you're probably wondering, what was this grand plan that got to the WHO Director General to convince everyone to eradicate smallpox? Good question. Let's talk about it. So, the general said that 1, there would be a vaccination campaign in every country to ensure an 80% level of vaccination immunity. And 2, a surveillance program would be instated, a non-creepy beneficial one, to obtain weekly reports of cases, and if cases were found, a 2 to 3 day intensive mass program of vaccination would be instated in the immediate area to prevent the infection from spreading further. It should also be noted that this strategy was largely aided in part by the work of Dr. Leslie Collier, who perfected mass production of a far superior freeze-dried vaccine that had a longer lifespan and could be used in warmer climates.
Smallpox vaccination versus variolation. Vaccination and variolation are both methods of introducing virus to the immune system, as seen in the photo, which boost the immune system and stimulate natural production of antibodies that combat disease. Variolation is the inoculation of the variola virus, while vaccination uses the cowpox virus. Inoculation is the exposure of live matter to the immune system. Variolation in America and Europe was puncturing of the skin and putting the virus in, as seen in the photo, while in Asia and Africa it was blowing of dried scabs into people's noses. The results of variolation ranged from a week of mild illness to death. The vaccination was created by Edward Jenner in 1796. Jenner took fluid from a cowpox blister, as seen here, and scratched it on the skin of an 8-year-old boy. 2 months later, he inoculated the boy to find that he was immune from the virus. Immediately after the vaccine became known, variolation was stopped around the world.
The enzyme-linked immunosorbent assay, or ELISA assay, is a test that measures the amount of a specific antibody in the blood. The first step in this test is to prepare your well plate by coating it with the antigens of whatever type of disease you're testing for antibodies with. Since the vaccine for smallpox is vaccinia, we are testing with the surface proteins of vaccinia virus as our antigens. The example of an antigen for vaccinia is hemagglutinin, which also exists in smallpox as well. This brings up an interesting point, because if you are either inoculated or have survived the virus, which are the same thing, you will have antibodies specifically for smallpox, which makes the ELISA assay very difficult because smallpox is both very dangerous to work with and rare. And so you'd have to end up synthesizing proteins instead of using the actual virus itself. The next step is to add the human serum, which is blood without cells or clotting factors. this serum hopefully contains antibodies to vaccinia, which will hopefully bind to the antigens. There's a very good chance that not all the antibodies will bind to the antigens, and so the next step is to wash out the wells with clean water to get out all the excess serum and antibodies. So now that we have isolated the antibodies attached to the antigens, we have new binding spots on the backs of all of these. And so what end up binding to these new binding spots here are the new antibodies we've taken from the animals. And the reason this is important, these antibodies are important, are because of this part right here, which is an enzyme that's chemically bonded to the animal antibody. The process for obtaining these antibodies is essentially putting the human antibodies into the animals and pulling out the antibodies that the animal produces to fight the human antibody. Much like the human antibodies, you have to allow the animal antibodies to incubate so that they can chemically bond to the human antibodies. There's a very good chance that not all of these animal antibodies will bind to the human antibodies. Like in the previous step, you wash it out again to get rid of all the extra antibodies. The steps we've taken so far haven't actually produced any visual cues of how much human antibody there is left in the sample of the human serum. And so the next step we take is adding a solution with substrate in it that will bind to the enzymes that we've chemically bonded to the animal antibodies. The substrate that binds to the enzyme will produce a change in color and absorption of the liquid that the antibodies are in. At this point, our well plate will look something like this, and hopefully we'll be able to see obvious changes in color. But to measure these very specifically, we'll use photospectroscopy to measure the absorbance of the solution. Now, obviously, they won't be different colors because they're the same substrate. So what we're really looking at are, take for example, assay 1 right here. This would be our vaccinia assay. And the reason they're different is because we should have tested the wells with different dilutions of human serum. So 1 to 10, 1 to 100, 1 to 1,000, 1 to 10,000, things like that. And so this will determine our titer, which is a measurement for a dilution. And so if it's a 1 over 100, it has a titer of 100, and 1 over 1,000 has a titer of 1,000. And so hopefully we're doing this just for curiosity and not because there's a new smallpox outbreak, but now y'all know how to test for immunity.